Hello everyone, this is the first talk of the theory lunch of the semester, and thank you for coming. This year I'll be replacing Pedro, so thanks to Pedro, who's not joining us right now, for a wonderful year of service to theory lunch, and me and Anish will take over this semester. So our first talk of the semester is by Paul Goelz, and it's about no stratification without representation. So I'll hand it off to him, and hope you enjoy.
Thank you, Raj. Everything I'm presenting today is joint work with Gerdus and with Ariel. I would like to start this talk with this image, which shows the current House of Representatives in this country. And these women and men are charged with representing the American people. That being said, you might already see, even like in the light conditions of this room, that this picture does not look like a representative picture of the American population. And there are multiple ways in which this is the case. For instance, women are underrepresented. Nowadays, they make up for about a quarter of the House of Representatives, but they have a slight majority in the population, so women are underrepresented. A similar thing can be said, for example, for age groups, where young people are vastly underrepresented in the House with respect to their share in the population, even their adult age population. So I mean, this way it's somewhat encouraging to see in the previous photo that some of the kids are also taking the vows, so who knows, maybe that's going to change, but for the time being, the House is much older than the population overall. These demographic groups are what we usually think about when we think about groups not being accurately represented. Racial groups, gender groups. But here's another group that I worry about just as much. For the last House of Representatives, the 115th one, this website down here went through the trouble of actually looking at all members, going through their comments and seeing whether they could be labeled as skeptics or outright deniers of man-made climate change. And at the time they found that the majority of House members held these views, even though polls pretty much exactly at the same time showed that the corresponding fraction in the population was much, much smaller and was a clear minority. So again, we have a disconnect. We have a lack of representation for people who believe in man-made climate change. And these opinion groups, what makes them very special is that they have such direct policy implications. Because of course, a House of Representatives here will vote very differently on a measure that is supposed to combat climate change than what the population overall might want. And I think this is a real problem. You can pick any opinion, any point of view that matters in the political area, and you can ask yourself whether you really have any reason to believe that the percentage of people in the House of Representatives, for example, who hold this view has anything to do with the corresponding fraction in the population. And I think this is a real problem. So before I even tell you what framework we're operating in this work, I would just like to fix this very high, very hard to achieve goal to more accurately represent unknown groups in the population. And this unknown here is key. Because if we only care about accurately representing women, we can impose a quota that works. If we only care about climate change deniers, we can at least attempt to impose a quota, which is more difficult. But the problem goes deeper, because by the time that we select the people in Congress, we don't really know what topics they will have to deal with. And even if we did, these topics would be way too many to impose quotas on all these opinions at the same time. So we really have a problem. And still we want to make some progress towards this goal. We believe that there's some framework where this is somewhat possible. And this is what I will begin this talk with. I will talk about this paradigm, which is called sortition. It's a paradigm of representative democracy. And I will just give you some context of what it is and why we believe that it should be taken seriously. Then the next point is I will discuss this tool, stratified sampling, which we think can be used to achieve this goal in the context of sortition. And we do a bit of, we do a fair amount of theoretical analysis there. But everything is just over worst case groups. So we finally have an experiment that I would like to share where we show that our theoretical analyses actually have something to do with this application that I claim of opinion groups in a population. Okay, let's head to sortition. Sortition, as I said, is a paradigm of representative democracy. And that means that we have this familiar setup. We have the people overall, and then we have a much smaller body of representatives. Why do we need that? Well, to really make effective policy, it seems that you really want to be able to exchange ideas, to make compromise, to have these ideas spread. And all of that, even given today's technology, seems to work much, much better in something that has roughly the size of a parliament or a Congress rather than the population overall. So I think there's a real value in having these representatives up here. The question is, how do we select them? And the only way that we really see in everyday life is to elect them. And we kind of think as this as being the only way of doing this in a democratic way. Advocates of sortition would disagree. They would say, why don't we just throw the dice and select a random subset of the people and make them our representatives? Now, that's kind of striking. And I think the urge is very much there to just say, okay, that is kind of crazy. We want good people, now we have random people. Is this really something we might want to do? And I would just spend the next couple of minutes trying to make a point that, that this is at least something to be reckoned with. First of all, I would like to take a bit of a step back and give you some historical context, because it turns out that this idea of sortition has a very rich historical precedent. And it actually goes back as far as our idea of democracy itself and dates back to ancient Athens, where especially in the 5th century BC, but then also the 4th century where we have more sources, sortition was a very instrumental tool for their republic. And now the way that I was taught about ancient Athens in middle school and high school was mostly from the point of view of a direct democracy. They had this institution, the assembly, where all the citizens, according to their definition, had the right to participate, and actually some fair share of them actually participated regularly. And they were the ones who voted on proposals, yes or no. That being said, there were other institutions that had very similar importance. For example, there was a People's Court, the judiciary, and there was the Council of 500, which, for example, set a lot of the agenda and actually elaborated the law proposals. And they were similarly important, and they were selected, they were filled with randomly selected citizens. So they used sortition. And this here is the tool that they used, a clariterion, which was a way of transparently at the time selecting a subset of the accurate size. Now, one might wonder whether maybe just people so far back didn't have available the tools that we have nowadays. Maybe they didn't know about the elections, and so they had this rudimentary way of governing their city. And at least this is not accurate. They very much knew about elections. Elections were around at the time. Many city-states used elections, and even Athenians used elections. They, for example, used elections to select their military leaders, where they really put a lot of focus on having the most qualified guy doing the job for kind of obvious reasons. But they felt that using elections for other magistrates, for example, would run the risk that the people would only choose between members of an elite, not really be in power. So the elite would be in power, and the people would get to break ties or something, or swing the needle a bit in one direction or the other, but wouldn't actually rule. And this is what democracy is about. So they made a very conscious decision to fill nearly all of their magistrates with randomly selected citizens. Then after the fall of the Athenian Republic, democracy, and thus also sortition, becomes more and more rare. Sortition didn't really feature in the Roman Republic, arguably because they didn't want that level of democracy. But for example, in the Republic of Venice, over 500 years, the Doge was selected through a very convoluted system of alternating rounds of elections and sortition. And they wanted this compromise because they definitely wanted their Doge not to just be some random citizens. They wanted the Doge to be more qualified. But they also had this problem that they had these competing factions and competing families, and these intermediate steps of sortition made sure that none of these factions could really just crush the others and manipulate the whole process. Still in 1772, Montesquieu, who is one of the leading philosophers in France of the Enlightenment and one of the precursors to the democratic revolutions that we saw shortly after, wrote that the suffrage by lot, so sortition, is natural to democracy, as that by choice elections is to aristocracy. This point of view had a very long continuous history since Athens, but completely got lost pretty much around the time of the American and French Revolution, where the founding fathers of both republics actually didn't aim for democracy in that sense. They didn't use the word democracy at the time. They wanted something where the people definitely had a say, but didn't have a direct role in politics. They wanted the will of the people to be mediated by especially qualified people. And so they went for elections, they went for aristocracy if you want, and so much so that over time this idea of sortition pretty much just faded from public conscience. Except for juries where they still appear. all of that is old history. And our societies nowadays are fairly different. So none of that is really saying that sortition should be something that we should really do nowadays. But apparently it was enough of a reason for people to experiment with that, to see whether maybe it would still fit our societies. And so for the last 40 years or so, on very different levels of the hierarchy, so in states, in countries, people have experimented for different, also working on different topics with sortition experiments. And I would just like to pick one which is very recent and give you some more detail, which hopefully will lend some credibility to the fact that sortition might be a valuable addition. So these fine people here are members of the Irish Citizens Assembly. They're 99 randomly selected Irish citizens, and they convened over 12 weekends between 2016 and 2018. This assembly happened because Parliament decided so, and the Parliament also gave them a range of issues of societal importance to debate. And the most prominent and most contested one by far was whether abortion should be legalized, which especially in Ireland, a traditionally very Catholic republic, was a very hot button issue, and Parliament frankly didn't want to touch that themselves. And at the time, abortion was very, very severely restricted, giving equal right to life to the fetus as to the mother. So these people, 5 of the 12 weekends, they discussed this topic. And because obviously these members were not chosen for their qualifications or their prior knowledge, they had to somehow get up to speed. So they were provided with informational material, which they read before actually going there. And then they had access to scientists, for example. They heard from women who had experienced themselves having abortions, and spoke to interest groups and everything, and then spent a lot of time just debating. And this debating process was structured very well, where these 99 people were subdivided into tables where they would speak among 5 or 6 people. There were professional mediators at the different levels. They would really try to ensure that every person would be able to have their voice heard, and that things wouldn't be just dominated by some person who is very good at speaking. And finally, after 5 weekends, they made a proposal to Parliament to allow unrestricted access to abortion up to the 12th week, which was way more liberal than outside observers expected the committee to decide, but also way more liberal than outside observers expected society as a whole to go along with. And in both counts, they were wrong, because in a 2018 referendum, 67% of the Irish people approved of this proposal, and so now abortion with these limits is legal in the Republic of Ireland. I don't think we should try to judge the system based on whether we agree with the outcome that was there in this very specific example. But one thing that really stuck to my mind was going through the material that this committee produced. And in particular, I went through a questionnaire that was handed out to these members just after they had made this proposal. And they individually and anonymously had the option of adding things that they didn't find in the consensus that was voted upon, that they would still want to be noticed by the public. And it was really impressive, because these people from all walks of life, so young, old, rich, poor, educated, less educated, they all made very nuanced points, at least the 60 or 70 or so that I read, and very, very different points. So to me, it really doesn't seem like maybe the scientists swayed the opinion, or maybe the moderators completely told everyone to have the right view. But actually, these people seem to have an exceptional grasp on the topic and an exceptional level of ownership, which I'm deeply impressed by. And I think there's no secret here that I'm pretty excited about this approach, and so are all 3 of us. And fortunately, it's also not just the 3 of us. There's a growing movement going out mostly from the political sciences and also reaching practitioners who want to push what sortition is used for right now and try to introduce that in countries all over the world. So much for politics. Let's maybe finally move to something that we're all more qualified to speak about, something more mathy. So what do we mean by representation? Let's assume that the square here represents the people overall, and that we have some subset of this population, let's call it M, that holds some opinion, say. And this is the complement. And now we have this panel that we want to fill, and this panel has a specific size, K, in this case 6. So the easiest thing that we can do is uniform sampling. We can just select some subset of size K uniformly from all the subsets and fill our panel. Now, one thing that we can obviously do is just count how many people on this panel ended up coming from M. And let's call this random variable U sub M, U for uniform sampling. In this case, it's 4. One very nice property that we immediately have is that we made sure that every person is selected with equal probability individually. So by linearity of expectation, we immediately get this, that the expected value of this representation variable is k, the size of the committee, times the fraction of m in the population. And this, from a mathematical point of view, this is kind of trivial. But it's also pretty striking if you compare it, for example, to the examples that I started this talk with, where women and young people were not misrepresented by chance as a one-off event, but where there's some systemic bias that decreases the representation of these groups. If you do sortition in this way, you will never have this systemic bias. That being said, it's only over expectations. And so what you actually will see in practice is not always this. You will see something like that where the distribution has this very binomial-like shape. It's not binomial, it's hypergeometric because we draw without replacement. And this distribution has quite a bit of variance, to be frank. So for example, in the Irish example, I did the math. And I think with like 15% probability, you have 55 men to 45 women. So with another 15%, you have the same situation the other way around. So with 30% probability, you have a gender imbalance that I would say is visibly unequal. And that can just happen because their committee was only 99 people large. And obviously, you could just scale up the committee, but there are very practical hurdles to that. Sampling is complicated, but then especially flying people in, accommodating them, and making sure that they can all participate in this process, paying for the people who facilitate the communication, all of that is frankly really expensive. So there's just some limit to how much you can scale it up and just use the central limit theorem for your purposes. Still, people in practice don't just want to go with that. And one thing that they do is that they use stratified sampling or stratification. So say that we're worried about this gender imbalance. One thing that we could do is just split up this population into two pools of women and men, assume that they have equal size, and just reserve 3 seats for women and 3 for men. And within each of these strata, we just draw a sample as we did before. Obviously, we can do the same game as before. We can count how many people on this panel overall came from M. Let's call this A sub M. And this time it's 3. And if we did the splitting and the distribution of seats here in the right way, we still preserve the property that every person is selected with equal probability. So this guarantee a priori over the expected value still holds. And we never want to go beyond, regress beyond that. But there's still some reason that this time we got 3 and the last time we got 4, and that this time this is exactly, or at least closer to what we would have expected rather than the last time. And namely, plotting the distribution, the orange distribution that we got now is sharper and has lower variance than the one we started out with. And this is not super surprising, because imagine the way that I drew it, M correlated very highly with gender. And imagine that the two completely coincide, then the distribution would just be a spike here at the expected value. And the less and less correlation we have, we smoothly go from the spike, from the spike to something broader. So it's not super unexpected, but it's still a real potential, because in politics so many things correlate. Your opinions will correlate with your demographics, and your opinions highly correlate with other opinions. So if we stratify by reasonable features, then hopefully every group M that we really care about will somehow correlate with these features that we stratified on, and hopefully we'll get as much of this like narrowing variance reduction force as possible, and we will get better representation without paying for scaling up the committee. That is the hope. The danger would be that maybe we can mess up the stratification, and maybe we can make the distribution wider. Maybe we can increase the variance.
It's worse though, right? You can't make it worse than the way it was.
Let's hope so. It turns out you can, but you kind of can't. Which is the best kind of answer I can give. The worst case would be if there's simply no correlation between the two.
Then it's the same, right?
It's kind of the same. Give me a second, I'll get to that. So this is the distribution we produce here, and it really looks a lot like the uniform distribution. But if you really zoom in, you will see this blue bar here. And that hints at the fact that we actually messed up the distribution a bit. So the original blue distribution was slightly narrower, slightly had lower variance than the one we produced. But fortunately, by such a low margin that I don't think it really matters a lot. And this margin is way larger in this toy example that I plotted here than it would be in the real world. So kind of yes, kind of no. But we want to prove that while unfortunately we can't prove that we can never do worse, we never can do worse by an amount that we would actually care about. This is maybe a short summary of our main result. So let's say that we live in a continuous world. And there it exactly holds what you said, namely we can just, and continuous world means that our agents come from a continuum. There it holds exactly what you said, namely that stratification can reduce the variance, never increase it. So here's some math. It looks more complicated than it is. So in a continuum, we just have binomially distributed variables. Let's look at the right-hand side first. We have k seeds, and each of these terms is for one randomly drawn person, which will come from m with probability m over n. So that is a variance of uniform sampling. And now let's say that we split up this pool into two pools, and the pools have sizes n1, n2, and contain m1 and m2 many people from m. And then we will just get this term over here because the two sides are independent. And just through easy calculus, we can show that the left-hand side is always less than or equal to the right-hand side. And that shows not just that at the highest level, it's never a bad idea to stratify, but you can also iterate this argument and just say any single stratum that you already have, if you further subdivide it, you can only win. Cut and dry. Yeah, we get that the variance of stratified sampling is upper bounded by the variance of uniform sampling. Yes?
What is continuous here?
Continuum, I just mean the voters that you sample are not discrete entities, but you just have this super large.
I think you just mean sampling with replacement, essentially.
Yes. Well, it turns out there's another complication. I'll get to that slide. Yes.
In the regime where your number of people is very large.
Yes, exactly. Maybe think of it as the limit as the number of people gets very high.
The number of people in the population, not
in
the
the
number
population.
on the committee.
Yes. The number of people on the committee stays the same in this case. And this case. Okay. Thanks for the clarification. So we happen to live in a discrete world. And there we have two complications. The one is that we sample without replacement. And it slightly messes up things, namely these terms that we had before from the binomial distribution now turn into these hypergeometric terms, which have this annoying thing over here. And this annoying thing is exactly what is to blame for the slight widening of the distribution. The other complication, and the more serious one, is rounding. Because it was awfully convenient that I assumed that both genders were the same size in the population, and that also my K6 was divisible by 2. If that had not been the case, then we would have to somehow randomly decide how many seeds to draw for every stratum, and we have to do that in a way that we still guarantee our probability of, or our equal probability of every person to be selected. And it's also kind of delicate because we care about the variance, and this rounding step will definitely introduce variance. It turns out that if you just use one of these off-the-shelf dependent rounding techniques, we have no idea how to bound the variance in a way that wouldn't completely blow out the kind of delicate calculation that we have here. And then we wouldn't get any bound that is very useful. So,
Can I ask you?
Yes, please do.
Okay, so the stratum, is that referred to, well, back up.
Yeah.
So far you only talked about one, what do you call it when you use gender to decide the two sets?
Yeah, and that would be the criterion, but the two sets are strata.
Strata,
Yes,
okay.
thanks. And choosing
You
how.
have
Yeah,
more than
yeah.
one. That's one.
Yes.
That's one classification. You could also use age. You could also use
Yes.
what,
Yes. So,
income or something like that, right? If you
yeah.
wanted to.
Yes, absolutely. That's just my running example, but the
You want to
stratification.
use a lot of that.
Yep.
You want to incorporate more of those things.
Yes,
right?
absolutely, and we will, I promise. So the stratification is the partitioning of our electorate into different strata. I'm sorry if the terminology wasn't clear. So I will just speak about the way that we do this rounding step. Not some off-the-shelf dependent rounding technique. We call it block rounding. It's not very complicated, actually. It just makes for pretty diagrams. So I'll try to explain what it is. Imagine that we just line up all our agents on one line. And we group them together by strata. So imagine these are women, these are men. I don't really know. Yeah, well, we have two more strata. And the lengths in this diagram obviously correspond to how many people are in there. Then we can draw this line every n over k many people that describe the boundaries between seeds. And what we do now is we look at every seed. And if the seed in this diagram is entirely contained in the stratum, we just draw one more person from this stratum. If the seed, however, is split in this diagram between two strata, then we flip a biased coin with probability proportional to this side here. We will give one more seed to the left stratum. With probability proportional to the rest here, we give it to the other seed. And that makes it fairly simple to see that the expected number of seeds that we will draw for every stratum is proportional to the size of the stratum. And within every stratum, we don't discriminate between agents. So that will be what still makes sure that our a priori guarantee holds, and that every person is selected with equal probability. Another thing that I would already like to point out, the reason why we do this kind of a convoluted thing is that certain correlations are very localized. So the number of the number of seeds that we draw from from this stratum here, for example, correlates with the number that we draw from this stratum, because there's one seed that will either go to the one or to the other. And it also correlates with the number of seeds that we draw for this stratum, but not with any other stratum. And this will be what allows us to do tighter bounds than just some dependent rounding technique. So now we're able to at least state the theorem, which is let this a sub m again be the number of a random variable denoting the number of people on our committee coming from the subset m, and we select this committee by stratified sampling using block rounding, which I just proposed. And we also have this innocuous assumption that every stratum is at least n over k, contains at least n over k people, which was the reason why in the previous example every seed was at most split by between two strata, and not really sure that it makes any sense to stratify further than one seed equivalent. So you can.
Strata and what are n and k?
N is the total number of people. K is the number of seeds that we select, and the number of strata is something independent. This assumption assumes that you can't have more strata than seeds. That's implied by it. It's weaker. And if we have this, then the variance of stratified sampling is upper bounded by the variance of uniform sampling. Well, that is up to this term here, which looks a lot like the term that we had in the hypergeometric distribution variance to the -1, because this is the place where we lost in the example that I showed you before. But still, if we're willing, so the good thing is this number is very close to 1 in practice. For example, for the island example, it's 1.00003, which is much less than in the example I actually plotted. We wouldn't be able to see anything here. And so if we're willing to not care about this factor, then the story still goes through. The stratification cannot increase the variance, but can decrease the variance. Yes, please.
So I'm still a bit confused.
Mm-hmm.
This is about, so the strata here refers to a partition of the population.
Yes.
A single partition.
Yes.
But I think it was earlier mentioned, you could have stratification based on different criteria, and you would want to somehow maybe achieve this representative property on all of them. Let's say age versus, gender.
Yes. And so the idea is you have one single partition. The theorem holds for any stratification that you can choose, and you can stratify based on very different things. You just have to give me some partition. And this guarantee holds for any stratification that you select, given that we have this bound here, and for any group M. And then if the two work very well together, let's say they completely overlap, and you just have some strata that are completely drawn from that completely consist of people from M, and some strata that completely don't consist of M, then up to rounding you don't have any variance at all, and you go all the way down to 0. But even in the worst case, you're always bounded by this thing. How much you gain, I will quickly speak about that later, but that will depend on how well your stratification and your M actually correlate. Yes?
So if you wanted to stratify multiple criteria, just be specific, say you had like 4 age groups and 2 genders you wanted to stratify by, that would end up with just 8 different strata, and as long as each of them was at least one,
and over k,
expectation, then it would work.
And you can define these strata as you want. You can define them by these intersections, but you can just give me any partition of the electorate that satisfies this assumption.
Okay, but on the other side, if the intersections were too small, you couldn't do it.
Then what you would do is just join some of them together and try to join similar ones together. But these are excellent questions. So I would like to go a bit into the details of how we prove that and just give you a rough overview. I hope I won't lose people, otherwise it's short. And I do this because I think that some parts of this proof tell us how we want to pick stratifications. So the variance that we compute in A sub m really consists of two parts. The first step was this allocation, this rounding procedure where we allocate the number of seeds that we draw to every stratum. And then there's the second step where we actually sample within every stratum, and then it only turns out whether we have more people from M or less people from M. And the law of total variance allows us to split up these two factors. So this, the outer expectation and the outer variance range over the rounding, whereas the inner thing just goes over the sampling within the strata where we hold the rounding fixed. And so intuitively, the left term here is really the variance produced by the sampling in the second step, and this is the variance produced, added by the rounding. And I will speak about the left term first, which is the easier to talk about. Because yeah, the variance inside we can characterize very well. It's these hypergeometric distributions as soon as we fix the rounding. And we will have to throw out these hypergeometric factors. But as soon as we do that, we're essentially left with the situation that we had in the continuous case. And so what we can show there is that this term here is upper bounded by this term. The left-hand side is the variance that uniform sampling would have if we were in the continuous case. And we also have this term here, which gives us some guaranteed reduction in variance, depending on how well we stratified. K and N I introduced, the sum ranges over all strata I. Ni was the size of the strata. And this epsilon I is defined like that. So Mi is the actual number of people from M that we have in the stratum. And this will depend on whether our stratification was a good one or a bad one. And this here is maybe how many people you would expect from M to be in the stratum if you only had the global concentration M over M. So I try to draw it as a picture. So let's assume that we again have the situation where M is half of the population overall. And we have a stratum here where we stratified very well, and we're very far away from that. There's a very high correlation. Then if you just project this half onto the size of the stratum, you will get this area here, whereas this is the real area, and then the difference between the two areas would be our epsilon I. And obviously, we gain more the higher the epsilon I squared are, and it's also divided by the size of the stratum. So this is the left-hand side. I will not go in as much detail for the right-hand side because it's somewhat messy. I would just like to speak about two factors that influence whether this term here will be larger or not. We call them alignment and adjacency. Alignment means that if these lines between seeds and the lines between strata line up very, very closely, then most of the time our bias coins will just end up in one direction. And so we don't introduce a lot of variance. The other thing is adjacency. Because note that the inner part here that we calculate the variance over is just the expected value over the sampling. So if we have two adjacent strata and they have the same and they have essentially the same density of M within the same ratio of M within them, then in this term it really doesn't matter whether this coin flipped to the left or to the right. We're equally likely to select someone from M. So if we have very similar strata next to each other, we will also introduce very little variance in this step. And then finally, we make use of this fact that I mentioned earlier, that many of these pairwise correlations are just zero. And this allows us to give a bound that looks exactly like what we have here. And this is really nice because it means that the variance produced in the rounding really dovetails into the slack that we have in this upper bound. And so we add them together, everything is wonderful. We just get the uniform variance, and we have this factor here because this is the variance in the discrete world, and this was the variance in the continuous world. And this concludes the theorem, so and it also concludes the very technical stuff in this talk. And I should mention that this analysis is tight. I should also mention that we have a slight variation of this proof where we make where we have a slightly larger lower bound on how large these strata have to be, and then we immediately get a guaranteed reduction of this shape even in our rounding setting in terms of variance if we stratify well. So what does this tell us when we are actually putting ourselves in the shoes of someone who wants to do a sortition experiment and has to select one of these stratifications? First of all, this theorem applies up to very small strata, much smaller than the ones we would initially come up with. It holds up to 1 seed equivalent, so maybe we should go for very fine stratifications. If you have a coarser stratification, we can again do the thing where we just iterate this argument, and we say, okay, within this stratum, you could have lower variance just by stratifying within this stratum. Another point, and this is very vague, and this intuition comes from these epsilon I terms. What we really want to do is we want to make these strata very homogeneous, so that any question M that comes along is very likely to split them very unevenly. So to polarize them, we call that. So hopefully there will be many strata that are full of M proponents and full of M opponents, and few of them that are just split very much like the population overall. And this is the part that is really hard to achieve because you don't know M. It's really hard to guess that, but this is the game that you're playing in your head when you're selecting a stratification. And then one more thing would be, for example, to make use of this adjacency fact. So we also have an idea of which of these strata that we produce are more similar. So it really makes sense to line them up in this diagram that I had from left to right, to line similar strata next to each other so that hopefully adjacency, will make sure that the variance introduced by rounding will be limited. These things were theoretical analyses and only held for, and all of them held for worst case groups M. But I claimed this application of opinion groups. And just because we have some analysis here, it's not immediately clear that this will be useful if you're really interested in the application. So this is why we did an experiment where we tried to make this connection and really close the gap between practice to theory by quite a bit. Our goal is to show that our findings can really be used to improve the representation for these unknown opinion groups. And for that we used data from the General Social Survey fairly recently on 2 different years where we used subpopulations of roughly 2,000 people. The size of the committee is set to 50 in both cases, which I feel is a good compromise. And this is what you should imagine this data set to look like. So we have many, many agents and we have many, many, many features because that's what the General Social Survey is good for. Now my role in this experiment was to curate some of these features. First of all, I selected 14 demographic features, which include age, education, religion, but really a wide range of things that you might expect to see here. And then the more interesting step was to also select features that talked about political attitudes. And I selected 10 for each of the 2 years and turned them into binary attitudes so that they actually define a group M. And so just random examples here are, is it ever okay for a policeman to hit a man? And should the government do more to combat wealth inequality? Should we spend more on natural parks? National parks, I believe. Yes. So we wanted that my collaborator, Gerus, is really in the position of someone who wants to do one of these experiments and who has to deal with all the uncertainty of not really knowing what they're optimizing for. So we gave him access to all these columns here that were demographic and to a random subset of the binary attitude features. And then we're supposed to give him some idea of the population he was dealing with and which of these demographic features really drove political opinion, give him some idea of what these attitudes might be like, but very crucially, he didn't have any access to the other columns. And not just to the content of the columns, he didn't know the questions that were behind these columns. And then he had to build a stratification that was supposed to perform well and give a large reduction in variance with respect to the 5 in each year non-revealed binary attitude features. What was he competing with? Well, obviously there was a benchmark of just uniformly stratifying or uniformly sampling. We also had a benchmark where we just stratified based on combinations of gender and race, such as Isaac suggested. And we also tested something where we just tried to use k-means clustering to get some. It's not very principled, but we thought maybe the computer might be better at finding logical subsections of the population, and maybe that would make for a good stratification. The measure that we're comparing on is the reduction in variance, really, on these unrevealed features. But the reduction in variance is very hard to interpret, so we can instead express it as a number of as the alternative committee size where uniform sampling would have the same variance on these features. So, for example, uniform sampling will always exactly give us the number of actual seats, 50. And if we have a number that's higher than 50, that means that we essentially get the same representation, and we're just as likely as get good representation as if we had added more seats, just we don't have to pay for them. Should the number go below 50, then we actually mess something up and we're paying for that. So, yes, and the variance is normalized over percentages. That's maybe worth mentioning.
Well, wait, can
Yes.
you go back to the four?
Mhm.
So uniform, is that the algorithm you described a little while ago?
Uniform just means you just select some subset of size k, and you don't.
So you don't
yeah,
use the stratification
yes,
at all?
yes.
Where's the one that uses stratification?
The manual one is a stratification. The gender race combinations are a very simple stratification, and the clustering also produces a stratification.
So you're not using stratification based on all the millions of strata that you defined in the previous slide? Because there's going to be a vector of bits there that are going to be many, many combinations, like
Yes.
age and all your opinions on these different issues,
Yeah.
right? There's going to be
The problem is you can't stratify based on, you can't make the strata so fine that every set of features, every combination of features only gives you one strata. Because then we widely violate this restriction that strata can't be smaller than one seed equivalent. You have to make some trade-offs, and so Gerdes made a trade-off in which of these features to use to build a stratification where he couldn't have more than 50 strata. And the clustering approach also tried to do something like that. The gender race combinations don't go that finely, but they're just a very simple way, and maybe that gives us much of the benefit already. That would be good to know. And yes, these are the results. As I mentioned, uniform sampling will look very boring here because it's always exactly at 50. This very simple stratification based on gender and race gives us some improvements nearly all over the place, but also very limited improvements. So usually one seed out of the 50, one seed equivalent. There's one case where we slightly regress beyond uniform sampling, but also not by much. The two other approaches are more successful, especially the manual one, where in 4 of the cases, 4 of the cases, we have more than 4 seed equivalents that are being gained, so more than 8% more of seeds without paying for them, which is kind of encouraging. And the k-means clustering is somewhere in between the two. Another thing that we looked at was the rounding, because the rounding was so crucial and was really the main part of the technical work. Was this really just an annoyance that we had to deal with, or is the variance introduced by rounding really something that we should care about in practice and that we have to look out when we choose a stratification? It turns out that yes. So these half-transparent extensions of the bars show how much more we would have gained if we hadn't introduced this rounding, this variance in rounding. And what we see is that k-means and the manual stratification really leave some variance on the some increases on the table here. And we have further analyzed where this variance is coming from based on our theoretical analysis. And the solution is fairly simple. The k-means approach didn't look out for either adjacency nor alignment. And so it loses on both counts. And the manual approach did a fairly good job at using adjacency. We placed similarly defined strata next to each other, but we didn't look out for alignment. And this is still, like in many cases, this is half or one seed equivalent. And so if we were to do the same thing again, I think we've learned some lessons that would allow us to get more out of this potential. This concludes the contribution of our paper. There's one more thing that I would like to mention before I stop, namely, in case you're interested in this idea of sortition, maybe from a computer science perspective, but maybe also just from a general political perspective, and you would like to learn more. I can warmly recommend this book by David Van Raybroek called Against Elections. And yeah, it's an easy read, and he makes a much more cogent case for sortition. So if you don't buy my story, maybe you'll buy his. And another thing there's really a trove of information is this blog called Equality by Lot, which seems to be the waterhole where nowadays all sortition advocates go to. And they make a very good job at tracking all the small scale events as well, where sortition is being experimented with, and they discuss the large questions as well. And there are very fruitful discussions that, for example, we mentioned our paper in a guest post a couple of weeks ago. More importantly, what do I want you to take home from this talk? There are 3 things, I think. The first one is that sortition is a pretty cool thing. From a computer science perspective, but also really from a political perspective. I would love to see more experimentation with that. And I could very much imagine that it's a valuable addition to our current system. The next point is our community also overlaps with artificial intelligence and ML, where fair ML, for example, right now is a very big thing. But often these fairness criteria are very simple. We just assume that we're given some specific groups, and as long as we do well to these groups, we've done a job. And I think often in practice, things are more complicated. Maybe you have a fuzzy notion of what groups you want to protect. Or maybe you want to, even like the gold standard would be, to give more guarantees that hold for arbitrary groups, or for arbitrary groups that happen to be somewhat coherent. And there are multiple lines of research in the different areas that we've been looking into that follow this thread, and I think that's very valuable. And then finally, if this is your goal, to represent more complex groups, especially if they're opinion-based groups, and you're willing to settle with a sortition, then I think stratified sampling can really help you. That's my talk, and I would love to take some questions. Yes, Deacon.
So you sort of gave proofs based upon the population. The population as a whole can't suffer very much from this rounding. Is it possible that a particular group, though, a particular subset, can suffer to a greater degree due to rounding than the population as a whole? Because that could then, annoy, depending on how you stratify, right? So I'm not quite sure how it would work, but it seems at least one person could have sort of bear the brunt of that whole, a lot of that effect.
Yes.
And so that person could then be very disadvantaged by stratification, whereas if it was uniform, they wouldn't be disadvantaged. Is that possible?
So, well, it's somewhat hard to frame this question even,
right.
Because we always preserve that every person is selected with equal probability.
Yes.
And usually when we talk about incentives, we make this very convenient notion that everyone's incentives are linear. And so you just care about your probability of being present there. You don't really care about, maybe you care about other people being present, but you don't care about the second order things. If that's true, then no problem. But there are situations where maybe that's possible. So I don't think it's really about fairness to single people, but for example to groups. You could imagine, let's say we live in this dystopic world where there's one very big political question and it's completely split. All women are for it, all men are against it. And our population is split 51% to 49%. Now, if we stratify by gender, and let's say we have 100 people, well, us men don't really have a chance. We'll always have 49 people on the committee. We'll always get outvoted, assuming that there's a majority vote. So in this case, we would really have an incentive, in this case, we don't want stratification to happen. This is not specific to the rounding, but I think the idea generalizes. So if you care about these weird threshold things, for example, you don't care about the expected number of people from your group who are on the committee, but you care about the number of times that you cross the threshold of 1/2, then you will have weird things, and I have no idea how to really get around them. But I think that just this expected value guarantee is a pretty strong guarantee, and so I'm not super worried about people really being harmed by the mechanism, and also about people really trying to manipulate the mechanism. Yes?
Could you go back to the slide with those bar graphs?
This one or the previous one? Yeah.
So what this is saying is that just at a high level, you've gotten the best possible, the example on this graph is going to something like 58 people. So in other words, with 50 people, your committee is as good as a random one with 58 people.
Yes. I mean, they're both random, but uniformly random, yes.
That's a little disappointing to me. I thought this would give you more leverage. You're saying it doesn't, in these real life experiments, it doesn't give you that much. I mean, it's a 15% advantage or something.
Yes.
It's not like 5 times as many people. I thought you'd get some kind of much more leverage out of it.
I mean, I definitely wouldn't mind having more leverage. Maybe if you stratify, you'll end up having better results. That's also completely possible. We have this one manual or 2 manual stratifications made by a single person to really speak on. So maybe someone who has more experience, maybe someone who knows the population better, maybe someone who already has an idea of which opinions will come up can get much more. That would be very cool. One problem is that, so I think there's a real obstacle here, which is that these correlations in politics usually are there, but they're not super pronounced usually. So for example, I looked for examples at some point of opinions that are split, say, by gender. And I think Trump approval is one of the highest ones, where I think it's 60 among men and 40 among women or something like that, which is really drastic and a higher gender gap than you've seen for a long time. But it's still only 60-40. And I think this will stand in the way if you really want like another order of magnitude of improvement. I would love to be wrong. Yes, Sam?
Is stratification gainable somehow by the population? Like, can people self-identify in a false way in order to gain the system?
Yeah, this is really going back to Zico's question. So let's imagine we are in this scenario. of men and women. If we as men only care about the number of people in expectation who will be there, then there's nothing you can do. If you happen to care about when you cross the threshold, so yeah, let's say it's 50% plus epsilon and 50% minus epsilon. If the stratification is fair and works well, then the smaller group will always lose the majority vote. So in that case, all men would prefer to pretend to be women, so that we have a random sample and where like half of the time, or nearly half of the time, the smaller group has a majority. So there is some amount of gaming that is possible. It's difficult to do that in practice, I guess, especially when there's many things involved, when you don't really know the exact numbers. When also these quorums, I mean, you really care about, especially in these deliberative concepts, context, where you don't just immediately vote, but you have some discussion. Then you probably care about how well your ideas spread and things like that. I'm sure that in principle there are some incentives there to manipulate. I don't think they're very pressing. Yes?
So another manipulation question. Like somebody has to select the stratum, and if it's manual, like the Pennsylvania State Legislature manually stratifies the electorate, and their motivation is very political. They want to maximize the number of candidates. So imagine I'm doing the stratification, and I want to maximize the number of Republicans or whatever.
Yeah. So if you're maximizing the expected number of Republicans, there's nothing you can do. And we can all trust